Hello friends. So today we will going to discuss some problems of chapter work, energy and power. Now let us start with a very simple problem. This is a block of mass 500 kg. Now if this block is to be lifted up, then it means the external force applied should be in this direction, because there is always gravity acting on it in downward direction. So if you want to lift something up, you have to apply a force against to gravity. So if the question says that you have to lift a block at a speed of say 0.2 meter per second, at this constant speed, then how much power you need to apply to lift the block up? What is the power being applied? So you can get this simple kind of question. Now what is the catch here? The velocity with which the block has to move upward is constant. So when the velocity is constant, it's constant only when the net force acting is 0. So the net force acting in 0 means what? Means the force externally applied by any agent to lift the block up has to be equal to gravity. Then the problem becomes very easy. We have read that work is equal to force dot displacement. And power we have read rate of change of work. It means power is equal to nothing but dW by dt. So if the force is constant, suppose, then displacement by time, derivative of displacement by time is what? Simple velocity. So your power becomes force into velocity. Now in this direction, the object has to be lifted in upwards direction, and the force external is also in upward direction. So just cos 0 1. Now this force is equal to what? mg into velocity v. So mass 500 kg into g, say 10 meter per second square, into velocity 0.2 meter per second. So this is going to be your watt. The SI unit of power is watt. That is joule per second. Very simple to calculate. This is around 1000 watt. So this much power of the machine should be. The machine, the external agent, whatever is providing this force, should possess this much power to lift this block of 500 kg in the upward direction at a speed of 0.2 meter per second. So very simple. Now we move to another problem of simple category. Just suppose the force given is in this form, 10 plus 0.2 x Newton, and we have to calculate the work done if an object is being carried from x equal to 0 to x equal to 5. So these two things are given, force and initial and final position vector. This is xi, this is xf, and we have to calculate work. Now force is a vector quantity, so it means there should be an I here. So it means it's the force along a direction, that is along x direction, and displacement is also along x direction. So work is simple. F dot del r. Now here we will integrate it. Why? Because the force is not constant. It is dependent on x. So we cannot take out this force F outside the integration sign. Rather we have to keep it inside the integration sign. So it means it becomes 10 plus 0.5x dx. And the limits will be the initial and final positions, 0 and 5. So if we simply integrate it, we will get work equals to 10x plus 0.5x square by 2. Limit 0, limit 5. If we just solve the limit, we will get 50 plus 0.5 by 2 into 5 square, that is 25. And the other part will be 0. So it will be simply 50 plus 25 by 4. So that is, we can simply add it. This is joule. Or 25 by 4 is simply what? 6.0 6.25 plus 50, 56.25 joule. So very simple, just we have to multiply it. We will do again almost similar problem. So this is the wedge, an angle of wedge is 30 degree, and the block is being pulled up at a speed of 1 meter per second square, acceleration of 1 meter per second square, and the block weighs 2 kg suppose, and the initial velocity of the block was 0. So this is the case being given to us, that the initial velocity of a block when it started at the bottom point was 0. It's moving at the incline of a wedge whose angle is 30 degree, and it's moving up at an acceleration of 1 meter per second square. Now we have been asked that what will be the power being supplied to the block at t equals to 4 seconds. Just at t equal to 4 seconds or 4 seconds, whatever. So at this point is t is equal to 0 and somewhere t is equal to 4. So our initial velocity is 0. So final velocity should be u plus at. Now here please keep in mind that we are not going to resolve the acceleration vector into its horizontal or vertical component. Why? Because we are interested in the motion along this incline. And this acceleration 1 meter per second square which has been given to us, that is simply along the incline. So we will get the velocity along the incline. It means just 0 plus 4 into 1, 4 meter per second. Now we have been asked that what is the power being supplied. So for that we need to find out the force, and that's again pretty simple. Since acceleration is already 1, mass is 2 kg, so force is m into a. means 2 Newton. So 2 Newton of force is acting on the block. But the catch here is that we have been asked to find the power of the machine which is driving this 2 kg block in the upward direction. Power of the machine which is driving 2 kg block in this upward inclined direction. So the 2 Newton force, which we simply found out by multiplying mass into acceleration, is this the 2 Newton force which is being supplied by the machine, or is it something else? So what we did in the first problem? In the first problem, the net force was 0 because the object was moving at a constant velocity. But here, the net acceleration is 1 meter per second square. So the force corresponding to this acceleration is just the net force. But in reality, there is a gravity acting on it and some external force is acting on it. So F net is basically F external minus F gravity. So what we have calculated is 2 Newton, that is F net. We need to find F external. So here you can see the gravity is acting this way, mg. So the component of gravity along this incline is what? If this is 30 degree angle, this is 90, it means this is 60. So the force along this direction, downward incline, that is 2g cos 60, and the force being applied by this machine is this force external. So 2 is equal to force external minus 2g cos 60. So इसलिए F external is equal to 2 plus 20 into half, that is 12 Newton. So this is the external force being applied to us, to the block basically. So now we have to find the power being supplied by the machine at t is equal to 4 seconds. So power will be simply F dot V. Both are in the same direction, so we can replace dot product by cos 0. So it is 12 into 4, that is 48 watt. So sometimes we have to keep in mind that what is actually being asked to us. Especially in the case of calculation of work of power, we need to take care of the thing that the work of which force is being asked. In the same problem, if we are supposed to ask the power supplied by gravity or the work done by gravitational force, so what we will take into consideration? We will take into consideration this force. I can see you same thing in another picture. This is the block moving up. This is force due to gravity. So what is the angle being made? This is the angle. So if this is theta, this is 90, this is 90 minus theta, so it is 180 minus 90 minus theta, that is 90 plus theta. So this is the direction of displacement, this is the direction of force. The work done is equal to F dot dr. It means Fg dr, and this angle is 90 plus theta. So cos of 90 plus theta means minus sin theta. So that will give you the work done. So like just like in this case, if we take into consideration the force of gravity will be mg, that is 20, and whatever dr is, and the sine theta. So theta here was sine 30 degree, sine 30 half into dr or del r. This is the work, that is 10 del r. This is the work done by gravity. And this work which we calculated, 48 watt, this is the work done by the external agent, external machine which is pulling the force, pulling the block up. So every time while calculating work, just take into consideration that which force is being asked for calculation of work. Sometimes, actually most of the times, they vary from force to force. So we can take into another example. Now when we started this chapter, that time I gave just an example. Let's suppose if I push this board, try to push the board along the wall, so the wall will not allow the board to move. So there is no displacement. But I am trying my best, I am giving all my effort, I am trying to push it, but it won't move. So am I doing any kind of work or not? So the definition of work says F dot dr, displacement, force dot displacement. Displacement 0, it means work 0. So as per physics, I am not doing any kind of work. But just imagine, you are trying to pull a very heavy stone and you are standing in sun. The stone is not being pulled by you, but you started all sweating. So did you do any work there? The block, the stone didn't move, but yet you started sweating. So did you do any work? So as per physics, if you did not do, then why have you started sweating? I mean, where your energy has been lost? So that's a good question to be asked. That we have seen by law of conservation of energy that if we supply some work, the energy transfers. If we do a positive work, energy raises up. If we do a negative work, energy goes down. That is simply law of conservation of energy. So our energy goes down trying to push a stone which is actually not being moved. So what is exactly happening? So exactly what's happening is that if there is any heavy stone and I am trying to push it, though my work is 0 because there is no displacement, I am applying some force. So at every instant of time, there is a friction force. Always keep in mind this friction force. So you apply a force 10 Newton, friction force applies 10 Newton. We move up to 20 Newton, friction force moves up to 20 Newton. Say we move up to 500 Newton, friction also moves to 500 Newton. But this is our maximum limit. I cannot apply force beyond 500 Newton. But friction can apply, say, 2000 Newton. Just suppose that mass of the block is 200 kg. So, or say 400 kg. Friction will be mu n, and mu is half. So 0.5 into normal, 400 into 10. So that gives 2000 Newton. So this is the case. So maximum friction is 2000 Newton, our maximum limit is 500 Newton. So when we are applying 500 Newton, it means friction is providing 500 Newton. So our effort is being cancelled by the effort of friction. And that is the point we are losing our energy. We are giving our effort. But since friction is also applying same effort, friction is doing what? Friction is also doing effort. So friction is applying same effort. So it's not allowing this block to move. So it's simple competition. If I take over friction, then the block will start moving. Then I can say that I am actually doing work. But beyond that point, all my energy is being wasted by friction. Friction is just allowing my energy to be wasted. So always keep in mind that if by applying force the body doesn't move, then it means there is some external agent, opposite agent, which is wasting the effort or the energy being supplied by us. So now we move to another kind of problem. Suppose when we go into motion of projectile, so this is the position initial, this is the position final. Now there can be simple questions, as if the initial velocity of the ball is v, its initial angle is theta, it goes to a height of maximum h, it covers a distance of r. So question can be that what is the work done by air friction? Work done by gravity is simple. We have already seen what we have to do for work done by gravity. For work done by gravity, we just need to take into consideration this displacement from which direction to which direction, from this direction to this direction, or okay, if in just 1 second we have to say that what is the work done by gravity, that will be simply 0. Why? Because the initial and final position along direction y, is 0. Delta y is 0. Delta x is r. For work done by gravity, mg into, since gravity is in downward direction, so the displacement which will be taken into consideration, that should not be perpendicular, and there is only perpendicular displacement. So work done will be mg dot del r cos 90, because displacement is in this direction, so that will be 0. But it will be 0 for the entire path. But we are just asked that work done by gravity for the first half, then it should be gravity downward, displacement upward, minus mgh. And work done by gravity for second half will be gravity downward direction, displacement also in downward direction, simply cos 0 mgh. So if we add these two, we get 0, minus mgh plus mgh 0. Now if we are asked what is the work done by air friction, so generally in most of the mechanics problem, kinematics problem, we ignore air friction, but sometimes such theoretical problems are there, and actually air friction is very much significant. So whenever there is air friction given any problem, please take it seriously. That is just not a minute quantity to be neglected. Yeah, we have to consider air friction whenever it is given in the problem. So suppose the air has friction, the air friction is being taken into consideration, then what will happen? Just like normal friction we say that it opposes relative motion. So air friction is no different. It's basically same. Friction has its properties same everywhere. Solid, liquid, gas. Slight properties might change. That is not to be taken care of just right at this level. The basic definition that it opposes relative motion, that will be equally same, valid everywhere. So we see that at this point, this is the direction of motion, so friction will be in this direction. At this point, this is the direction of motion, so friction will be in this direction. At this point, this is the direction of motion, so friction will be in this direction. Now since the body is actually moving, so when the body actually moves, so it means it's a kinetic friction. It's simply the maximum friction the air can apply. So if we are asked to calculate the work done by friction, then how will we do? In that case, either a constant value of friction would be given to us, that this is the constant value of friction. We need to just integrate it. So for that, just take into consideration a small path for which the direction of friction can be considered as constant, and we have to integrate for that small path from this position to this position. So basically we will first calculate dW, work done by friction, dW for a small path, friction dot dx. Mostly we will replace the sign by minus because it will be considered just opposite to this at 180 degree angle. Whatever the value will be should be integrated from this position to this position. Or to make things simpler, what will be given, that suppose that this part, this track is part of a circle. Just suppose that this part is a part of circle. So in that case, this dx can be replaced by r d theta, and r will be the radius of the circle, and theta will go from 0 to 90 or pi by 2. Now if f depends on r or theta, r is fixed, so if f depends on theta, we will take it inside, otherwise we will take it outside and we will just integrate and put the limits. So why was it important? Only because in certain case we could deploy it, because we simply cannot put the limits, just the initial value or the final value of x, and take, even if f is not dependent on dx, we cannot take it outside and simply integrate it, because this is not a conservative force. Only in the cases of conservative force, the work done is independent of path. Say like this, suppose. So this is track 1, this is track 2. The initial limits x and f will be same. Suppose that friction is constant everywhere. So f will be replaced by any value, any numerical value. The initial limits and final limits are both same. Dx limits, xi and xf. So if we simply integrate it, then work done by friction here and work done by friction here, Wf1, Wf2, both will come same. But they are actually not same. The path lengths are not same. So when path lengths are not same, it means work has to be different, because it's a non-conservative force, it's a path dependent force. So that's why we need to have the actual length of the path. So in simpler cases, when this path can be considered as a circular path, then dx will be replaced by r d theta, because we know that if this is the arc length dl, and this is r and this is d theta, so dl is equal to r d theta. This relation is very much useful in solving lots of problems, especially of this chapter, work energy power, and other chapters as well. So then we get the actual length of this path. So then we will integrate it, so we will get the result. For different tracks, this r value will be different. So then we will get an actual result. So always keep in mind that if friction is playing any role, then please take into consideration the actual length of path. Just don't solve the problem taking into consideration the initial or final points. Such questions can be asked in conceptual forms or numerical forms anyway, but please take into consideration that if the force is non-conservative, then path length will decide the amount of work. Thank you.